All right, starting out homework number 9 with some conceptual questions here. So we have Nolan and Cy throw a ball horizontally at two different speeds from the same height above the ground. Nolan throws his ball faster than Cy throws his ball. So I'm just going to draw the paths of the two. So we'll have the one in blue and the faster one here in red. Okay, we want to know which baseball will hit the ground first. Well, if we think about their motions, they both have the same delta y. They both have the same initial y velocity, which is 0. And they both have the same acceleration in the y direction, which is negative 9.8 meters per second squared. So even though in the x direction, one is traveling faster than the other in the beginning, everything about their y direction is identical. So they're going to hit the ground at the same time. It's the same idea as the drop bullet and the fired bullet, the same idea as the demo we did in class with the drop and shoot. Now for B, we want to graph their two velocities. So we'll start with the horizontal direction. We know that for projectile motion, in the x direction, objects travel with a constant speed, so we're thinking about a horizontal line. The key difference here is one horizontal line is going to be at a greater y value than the other because it's traveling faster. So our y lines might look something like that. Again, two horizontal lines, but one moving at a greater speed. In the y direction, we already talked about how they're identical. So we're starting with 0 velocity initially, and in both cases, there's going to be a downward negative slope. I drew it a little bit above the x-axis, but it should just be downward. And those two lines are the same, okay? Both a slope of negative 9.8 and starting at 0 initial velocity. We have another conceptual question here. We have a person standing in an elevator holding a bow and arrow, and they're going to fire the arrow horizontally. Point A is a point directly across from where the arrow is being fired on the wall. So we want to know if, when we fire that arrow, if it will hit above, below, or at point A, if the elevator is at rest. Well, if the elevator is at rest, we know that as soon as that arrow is fired, even if it's fired horizontally, it's going to start falling. And so for the first one, it's going to hit below. Moving on to our second situation here. Now we have an arrow or the elevator is in free fall, okay, when we fire the arrow. So if that's the case, right, both the elevator and the arrow are accelerating down at 9.8 meters per second squared. So what's going to happen is, although the arrow is going to fall, all right, and take it past something like this, this point is also going to fall and meet up at the exact same point. So this is going to hit the wall at point A. In our third situation, the arrow, of course, is accelerating down at 9.8 meters per second squared, but the elevator now is accelerating upward at some rate. So when that arrow is fired, again fired directly at point A, what's going to happen is the arrow is going to travel and curve down, but point A is actually going to move up because the elevator itself is accelerating up. So this one is also going to be a case where the arrow will hit below point A. In that, we kind of answered question B as well. Will the arrow fired while the elevator is accelerating up, so this case, land above or below the point where the arrow fired while the elevator is at rest lands? So we already said that since point A itself is moving up, that just increases the distance below point A that arrow will hit the wall. All right, so the arrow fired while accelerating up will hit below the location of the arrow fired while the elevator is at rest. Okay, moving on to question 3. A projectile takes the path shown below. It passes by 3 different windows that are all identical in size. And we want to rank the time from least to greatest that it takes to pass each window. Well, if we think about our velocities at each point, so at A, our velocity is something like that, at B it's something like that, and at C it's purely horizontal, we keep in mind that the x component of that velocity as we go through, okay, remains the same, even though the y component changes and eventually reaches 0 at the peak. That means, okay, if we think about this horizontally, all of these windows are the same distance, the same width, okay? And this object, no matter what the y velocity is, the x velocity remains constant. So if it's traveling at the same speed horizontally each time and has to cover the same distance horizontally, that means that the times are all the same. Moving on to part B here, if we want to rank from least to greatest the average speed of the projectile, we just figured out that the times are all the same. Right? And we keep in mind, I know this is going back a few units, but average speed is simply distance over time. So all of these times here were the same, so we're really concerned about which one covers the greatest distance, and that is going to be window A. All right, clearly takes a longer path to get by A. All right, so A is the greatest, B is the second greatest, and the average speed at C is the least of all three. So there's your ranking. The other way to think about this is the fact that the x components here remain constant as it goes through this flight, but the y component is simply decreasing the entire time. So the magnitude of the velocity, which is the speed, okay, is going to get slower and slower as it rises up to its peak, which means the average speed for A will be greater than the average speed for B, which will be greater than the average speed for C. So here we have our ranking from least to greatest. Moving on to some of these algebraic problems, we're going to start with this one. We have an object launched horizontally at a speed of v off of a cliff that has a height of h. So here's my cliff with a height of h, and my projectile is going to be launched off of it horizontally with a speed of v. All right, it's going to fly through the air and eventually land on the ground. So a few questions we have about this: how long is it in the air? How far does it travel horizontally? And what is the magnitude and direction of the velocity when it lands? So now that I have my picture here, what I'm going to do is set up my chart in both the x and y direction. So I know, of course, that my x acceleration is 0, and in the y it's negative 9.8, which is negative g. I'm going to leave it as all variables for this problem. I'm launching at a speed of v, that's my horizontal velocity, and since it's fired horizontally, that means that my y velocity is 0. I also know that I'm starting at a height of h and landing on the ground, so my change in y is going to be negative h, negative because it is dropping. I see that I have a good amount of information over here on my y side, so I'm going to set up some equations with that and use that to find time, because we are looking for how long the object is in the air. So I have my delta y equation. That first term goes away because my initial y velocity is 0. And then I have negative h equals 1/2 times negative g times t squared. I'm going to multiply by 2 and divide by negative g, and I get 2h over g equals t squared. So that means that t is the square root of 2h over g. And there's my answer to part A. Moving on to part B, how far does the object travel horizontally? In that case, I'm going to go ahead and use my x equation. So in the x direction, I'm going to have my delta x equation. I know that acceleration is 0, so that entire second term goes away. And I find that delta x is just going to be my initial velocity in the x, which is v, multiplied by that time, the square root of 2h over g. Really nothing more I can do to simplify that. That's just going to be my answer there to part B. So for part C here, I want to think about the magnitude and direction of the velocity when it lands. I'm going to be thinking about first figuring out what my VFX and my VFY are. VFX is pretty easy. That's still going to be v, because in the x direction we travel with constant velocity. So I have that x component there, v in the x direction. I'm also going to have some y component going down, but I don't know what that is right now, so I'm going to have to go ahead and solve for VFY. So in order to solve for VFY, I can go ahead and use the VFY equation. And so I find that VFY is equal to, it's just going to be AT because that first term goes away, so negative g times the time, which is the square root of 2h over g. I can plug that into my triangle over here, and so I'm not going to put the negative in because I already have that arrow going down, but this y component is just going to be g times the square root of 2h over g. I can now go ahead and use my Pythagorean theorem and some trig to solve for both the hypotenuse here and also to solve for the angle that it makes relative to the horizontal. So I can go ahead here and use my Pythagorean theorem to solve for this. So I have v squared plus that quantity there, g times the square root of 2h over g squared, and that's going to be equal to c squared, which is my hypotenuse. I go ahead and do some algebra here, so I have v squared plus g squared times 2h over g, and that squared and the g are going to cancel out there. And then that final value for c here is just going to be the square root of that term, so v squared plus 2gh. So there's my hypotenuse. To go ahead and find the direction, I'm going to use tangent. So I'm going to say tangent of the angle equals opposite over adjacent. So tangent of theta is equal to that y term, g times the square root of 2h over g all over the x, which is just v. So that means that theta here is going to be the inverse tangent of that quantity, g times the square root of 2h over g all over v. I can do one thing, and that is I can move that g inside the radical. And so what that ends up doing is that top part becomes the square root of 2g squared h, because when I move it inside, it becomes g squared all over g. And then I can cancel out one of the g's, and it leaves me with a slightly simpler answer, although if you had left it like that first answer, that would be perfectly okay. But the simplified answer is the inverse tangent of the square root of 2gh all over v. For this next one, I have a cannon launched at an angle from the ground. Similar to the last problem, we have a bunch of things we need to solve for in terms of this cannon. So I'm going to first draw a picture, and then we'll think about setting up our two charts. So there's my picture. The cannon is launched at a velocity of v at an angle of theta above the horizontal. And it's going to fly up through the air, eventually landing on the ground. First thing I'm going to do is I'm going to break that initial velocity into its x and y components. So in the x direction, I have v cosine theta. In the y direction, I have v sine of theta. Alright, so I always know my x acceleration is 0 and my y is negative g. I just solved for my initial velocities in both the x and y direction, so it's v cosine of theta in the x and v sine of theta in the y. That's really all I know for now, but I can go ahead and think about some of the concepts I know. So I know at the peak, I know my Vy is 0, and my time here is half that total time. I also know that when it returns, when it lands, my delta y is 0 there, and my velocity is the negative of the initial in the y direction. So this is going to be negative v sine of theta. I could use either set of concepts. However, what I'm going to use is I'm going to use the stuff I know about the peak, because the first question is asking about this maximum height. So I'm going to be thinking about the portion of the launch from the ground up to the peak. That's the part that I'm really going to care about. And I'm going to say that my final in the y is 0. So I'm going to go ahead and use that y side to solve for my maximum height, because I do have 3 pieces of information in that y direction. I'm going to use my VF squared equation. So 0 is equal to v sine of theta squared plus 2 times negative g times delta y, which is that maximum height. So if I go ahead and solve for that maximum height, I end up getting that delta y is going to be equal to v sine of theta squared all over 2g. So there I have an expression for my maximum height. Up next, I'm going to be looking for the total time that the cannonball is in the air. So I'm going to stick with my y side and use my VF equation now. So I'm going to say 0 equals v sine of theta minus gt. And so that means my time here is going to be v sine of theta all over g. However, that's only half my time. That's only the time to the peak. And so to get my total time in air, I'm going to multiply by 2, and that means that my total time is going to be equal to 2v sine of theta over g. Moving on to C, what is the range or the total horizontal distance traveled? For that, I'm going to go to my x side and use my delta x equation. I know that that final term just goes away because my x acceleration is 0, and so I find that my delta x is just going to be v cosine of theta, which is that initial velocity, times that expression I just got from my time, 2v sine of theta all over g. I'm going to go ahead and rearrange that slightly, and so I get that delta x is equal to 2, and it's going to be v squared because I have two v terms here, times sine of theta times cosine of theta all over g. And if you leave it just like that, that's a perfectly acceptable answer. There is that trig identity that 2 sine theta cosine theta equals the sine of 2 theta. And so we could use that and substitute in, and I could also say that delta x is equal to v squared times sine of 2 theta, right? There's my 2 sine of theta cosine theta, all over g. So either one of those is perfectly acceptable. You're certainly not expected to know that trig identity off the top of your head and be able to simplify with it. Moving on to the last part, we want to know how fast the cannonball is traveling, both the magnitude and direction when it hits the ground. And so we know in the x direction it's going to maintain that speed, so my vfx is still going to be v cosine theta, traveling to the right, and my vfy is going to be v sine of theta, but now it's going down. We know that that y velocity is the negative of the initial when it lands. Now I could go through and actually solve this out with the Pythagorean theorem and some trig, but the easier way is to notice that this triangle here and this triangle here, the triangle when it launches and when it lands, are identical except the fact that this y component is just flipped. Okay, it's the exact same thing but flipped. So that means that the magnitude is still going to be v. Same magnitude, it's just the triangle's flipped. My angle is still going to be theta, it's just now theta below the horizontal instead of theta above the horizontal. So my final velocity when it lands is v at an angle of theta below the horizontal. Okay, just flipped from that initial velocity. Moving on to this next one, we have two hooligans who are on top of a bridge launching water balloons at a train that's passing by below them. The bridge is a height of h above where the train is. We launch the water balloon when the train is directly below them. So we want to know what angle to launch them at. We launch the water balloons at the speed of vb, and the train's traveling at this constant speed of vt. Okay. So there's a long, complicated mathematical way of doing this where we're setting up our projectile motion, we're setting up a kinematics for the train, we're writing multiple equations, combining them, and solving. And that's fine if you really feel like doing that, but there's a much easier way of doing it, just thinking about the motion of these two objects. So the train is going to start here and travel some distance x. Okay, the balloon is going to fly through the air and land on that train after it travels that distance x. Well, we need to think about the thing that really matters here is that the train travels a distance x in some amount of time t, and the balloon, thinking about its horizontal motion only, is also going to travel that distance x, and it's also going to take that same amount of time t, because they're both starting at this point when the balloon is launched, and they both land or both end up at this point when the balloon hits the train. So they travel the same horizontal distance in the same amount of time, which means they have the same x velocity. Okay, that's the key to this problem. They have the same x velocity, and more importantly, the balloon is traveling at a constant velocity, okay, in the x direction. That's a concept we know from projectile motion. So as long as the x component of this velocity of the balloon is the same as the velocity of the train, the balloon and the train will always be directly above each other. At every single point that the balloon is throughout the air, the train will always be directly below it because they're traveling at the same horizontal speed. So I'm going to think about that initial triangle for the balloon. I'm launching the balloon at some angle theta with a velocity of vb, and I know that I need to make that x component be equal to the velocity of the train so that it stays directly above the train. And then there's going to be some y component that we really don't know, nor do we care about. Based off of that, I can say that cosine of that angle is equal to the adjacent side, which is VT, over the hypotenuse, which is that VB. So cosine of the angle is just going to be VT over VB, which means the angle I launched the balloon at is just going to be the inverse cosine of VT over VB. For this next one here, I'm going to be going ahead and I'm going to be comparing the flight of a soccer ball on Earth to the flight of a soccer ball on the moon. In both cases, we're launching this ball at some velocity of v at an angle of theta above the horizontal, and it's going to fly through the air and land on the ground over here. So that's going to be the same whether it's on the Earth or the moon. The other thing I'm going to do is I'm going to break that initial velocity into x and y components. So we have v cosine theta and v sine theta. So what I'm going to do now is set up a chart here, one for the object while it's on Earth, and another for the object while it is on the moon. So we just found the initial velocities in the x and the y direction, and that's going to be the same for both Earth and the moon. Okay, it's both going to be v cosine theta and v sine theta. We know our x velocity, x accelerations in both cases are 0. The one thing that changes here is the y acceleration is negative g on Earth, and on the moon it's going to be negative g over 6, because it's 1/6 the acceleration due to gravity. First question here asks us to compare the total time in air for the two objects. So I need to go ahead and think about what other concepts I know, and these are going to be the same for both the moon and Earth. In both cases, the Vy at the peak is 0, and the time is half the total time. Now, what the value of that time is may vary, but in both cases, it's half the total time on that planet/moon. And I know when it lands, my y displacement is 0, and my y velocity is going to be the negative of the initial, so negative v sine of theta. Since I'm mainly concerned with stuff when it lands, I'm going to be considering the entire flight of this object in this situation. So I'm going to say that my final velocity for both is negative v sine theta. Setting up my VF equation in both situations, I have negative v sine theta equals v sine of theta minus gt. So that means on Earth, when I go ahead and solve for t, I find that my time is going to be equal to 2v sine of theta over g. And for the moon, I have negative v sine theta equals positive v sine of theta minus g over 6. And I'm going to say times t m, the time on the moon. So solving for that time on the moon, I see that ends up being 2v sine of theta all over g over 6. If I get rid of that double fraction, I get that the time on the moon is going to be 6 times 2v sine of theta all over g. Comparing these two, I can pretty easily see, especially the way I wrote it here, this is just the time on Earth right here. So that means that the time on the moon is simply 6 times that. And so my final answer here is that the time on the moon is 6t, 6 times the time on Earth. Moving on to part B here, I now want to compare the total horizontal distance traveled. And so for that, I'm going to be thinking about my x directions. So what I'm going to do here is I'm going to go ahead and set up my delta x equation. So when the object is on Earth, its horizontal displacement is going to be the initial velocity v cosine of theta multiplied by the time. And I'm just going to leave it as t, and I'll explain why I'm doing that in a second. I do know I have another expression for it. That entire end to that equation goes away because the x acceleration is 0. On the moon, I'm going to say delta x m for the horizontal displacement on the moon, and that's going to be equal to v cosine of theta. And now I'm going to put in for my time, I'm going to put in 6t. I know that the time on the moon is 6 times the time on Earth, so I'm going to put that in as 6t, and that second term goes away once again. We can rewrite this with the 6 out in front, so it's going to end up being 6v cosine theta times t. And when I do that, once again, I can pretty clearly see that this right here is the same as Earth, And so I know that on the moon, my horizontal displacement will be equal to 6 times the displacement on Earth. Okay, for the last one, I'm thinking about the magnitude of the final velocity when the object lands. So on Earth, I know in the x direction when it lands, it's traveling at a speed of v cosine theta, and in the y, it has a speed of v sine of theta going down like that. On the moon, I know in the x direction, it's traveling at a speed of v cosine of theta when it lands. In both cases, that x is the same because we're not accelerating horizontally. And in the y direction, it's the negative of the initial, which is v sine of theta going down. And so I see that this velocity on Earth and this velocity on the moon have to be the same because their y and x components are identical. So for c, I can just say that the velocity is equal to the velocity on Earth.